Thank you. Great to be here. I'm live from Mountain View, Google headquarters. And you heard a little bit from Paige about where we are today with code in the PaLM 2 model. And I want to step away from that a little bit and imagine where we might be in the future. And to do that, let's start with where we are today. With traditional programming, you instruct a computer through a programming language. But programming has evolved today from where it was a few decades ago. It used to be primarily a mathematical science. And now so much of programming is more of an empirical, almost a natural science. It's probabilistic. It's dealing with uncertainties in the world. It's observational. And we train it through examples of showing it the kinds of things it should do rather than saying step by step, here's how you should do it. So that's a change in how we do things, and we need tools to keep up with that. I want to just show you the type of progress we have. So here's, you probably recognize this is the next KCD cartoon. This is from 2014, and it's sort of emphasizing the lack of communication that sometimes happens between a programmer and a manager. So here the manager is saying, we want an app where you take a photo and check whether you're in a national park. And the programmer says, sure, that's simple. I can do that in a few hours. And then check whether the photo is a bird. And in 2014, the programmer says, oh, well, that's a research team. It'll take me 5 years. But in 2021, this guy says, well, I can do it in 60 seconds by calling out to these generative AI models. He may have exaggerated a little bit. Looks like the video is actually 1 minute and 8 seconds. So close to a minute, but maybe a little bit more. So we've come a long way. There's so many things we can do now, but we need a way to be able to call and put all these pieces together. So I think in the future, programming is we're going to think of it more as a collaboration rather than an instruction. It's not the programmer telling the computer what to do. It's the two of them working together to explore the space of the problem. We want the computer to automate more of the task, but we don't want to give up that control. In fact, we want the human to have more control over the task. So the computer's doing more and the human's doing more. We want the communication to be more natural. Yes, some of it may be in a programming language or other formal languages. Some of it may be in natural English. Some of it may be in diagrams and so on. And we want that to flow back and forth. We want there to be more feedback from the program on what's happening from the users. We want to be able to explore choices faster and respond to change. And we want more evidence of correctness. So right now, we have test suites and so on. We want to do a better job of that to eliminate bugs. Now, a lot of the emphasis we've seen so far has been on code. How do we write new code with these large language models? But as developers, you know, that's a small part of the task. And in this breakdown, it was about 1/3 was writing code. And the rest of it, we don't have as much support for. So we need to concentrate on that as well. Just writing code is not enough. And the types of problems we're dealing with are different. You know, it used to be the typical problem was you write software for a bank and there's 1,000 different regulations and you got to get them all right. But in the end, there is an exact answer down to the penny of did I balance everything properly? Now we're dealing with problems often called wicked problems, where there is no clear problem definition, there is no clear solution, there's many factors and multiple stakeholders that come into play, and you have to please all of them. So just defining the problem can be hard, let alone trying to solve it. And that's the kind of thing we want to provide support for. Now, over the last year, several people here, Andrei Karpathy was one of them, saying, well, the hot new programming language is English. And there's definitely something to that, but English by itself is not enough. But let me give you an example. So this was several years ago. I got an alert on my phone, says, depart now for return rental car to Logan Airport. So I thought, well, this is great. It's a very nice integration. This is not AI. This is before AI. So this was just traditional programming, but somebody had to parse my email from the rental car company and coordinate that with the calendar and the maps and the alerts on my phone. And that was all done just right. But then they had to spoil it all by saying time of travel, 23 minutes by bicycle. Now, in some sense, that was a good suggestion because I commute to work by bicycle most days, and it's about 23 minutes. So that makes sense. But it didn't really understand what it meant to return a rental car. And so whose fault is that? Well, if I look at how the program was specified, nobody's job was to parse and understand what the event was. It was just to put the right events, the right maps up at the right time. So everybody did their job right, but it still failed. It's because the world is open, and we thought that this was about calendars and maps and events, but it's really about anything that could happen anywhere in the world. And so no traditional programming approach could handle all those possibilities, but maybe this AI-based approach can, and that's how the world has changed. I started to ask these large language models if they could do this, and a couple of months ago, all the models failed. You said, I have to return a rental car to the airport. Should I go by bicycle? And they all said these kind of hedge things. Well, it depends on many factors, the distance, the weather, and so on, because they're trained not to give bad advice. But this last month, finally, I get barred to say, no, you should not go by bicycle. So these models are continuously getting better. So how can we combine the best of these large language models to handle these open world wicked problems with traditional programming languages where we have some idea of correctness? Now, the eminent computer scientist Edgar Dijkstra said, in the discrete world of computing, there's no meaningful metric in which small changes and small effects go hand in hand, and there never will be. And if he's right, then gradient descent that we use to train these models is doomed, because how do we make a large language model better? Well, we notice an error, we make a small tweak to one of the parameters, and hopefully that decreases the total error, and we keep on making those small changes. But Dijkstra's saying that won't happen. And he's got a point, right? So you take a program, you change one bit in the program, and it could do something completely different. So maybe that means that the neural net will never write code. On the other hand, Arthur C. Clarke said, when a distinguished elderly scientist states something is possible, he's almost certainly right. But when he says it's impossible, he's very probably wrong. So maybe Dijkstra wasn't quite right. And Ken Thompson, one of the developers of Unix, said, when in doubt, use brute force. And our TPUs say, yeah, I got this. So even though it is really difficult to explore this space of programs and one bit can make a big difference, it's still possible and it still works most of the time. Chris Peach teaches the introductory computer science class at Stanford, and he says large language models solve 100% of the exercises. And we've seen multiple types of approaches to this. I want to look in depth at Deepmind's AlphaCode. And here's a sample that they solved. So the problem is described just in terms of informal English, and there's a couple examples of input and output, and now you have to write a program to do that. I won't make you read all this, but I'll say very quickly how this problem works. So the idea is you're given two source strings, a source and a target, and it's asking you, can you produce the target string by typing the input source, except that for some of the characters, you can replace it with a backspace. And that backspace means that you don't see that character and you don't see the previous character if there is one. So if you got ABABA as an input, you could type 3 backspaces followed by the B and an A, and that would give you the target. So you should say yes. There's other possible places to put in the backspaces that would give you the same result, and the answer should be yes regardless. Now here's the program that AlphaCode comes up with, and it gets the right answer. So that's pretty impressive, and it's not that long a program and not too hard to follow. But I decided, well, I'm going to do a code review. So the first thing is, if a novice programmer had written this, the first comment would be, well, you have to document this. Put in doc strings and comments for your functions. And maybe it's better to make this be a function and not straight line code because it's easier to test functions. And little things like just the spacing goes against the PEP8 Python standard. And the variable t is used for two different things. That's not great. And these one-letter variables maybe should be more descriptive. And these 10 lines are a little bit verbose. And here's a strange thing. So they set up this variable c, which looks like it's going to be used as a stack. As you pop things off of b, you store them on stack c. But then stack c is never used anywhere else in the program. And so I think what's happening here is it's been trained on past programs. It identified that this problem has something to do with stacks. That was great. And it says, well, often when I'm popping things off one stack, I save them someplace else. So let's do that just in case. And then it never went back and recognized that it didn't need that stack C after all. And then it's an inefficiency here in doing the popping, a little bit of verboseness. And when I look at this, I see this Lake Wobegon effect of half the programmers are below average, so half the output code is below average. And there has been some attempts to say, can we train these models on only on more high quality stuff? But it looks like we're kind of right in the middle, and we want to do better than that. So the question is, how can we get there? So here's an imaginary collaboration with some future automated programming tools, some add-ons to POM2 and to AlphaCode to make it better. So say it produced that first result. I want to be able to say to it, so I know this problem came from a programming competition, and often people in programming competitions go as fast as they possibly can. And don't bother encapsulating it as a program, but I want you to do that. And I want you to put in the doc string. So it can do that for you. And then I can say, well, your code's a little bit confusing and it's not obvious that it's correct. Can you show me another version that is obviously correct, even if it's inefficient? And so here's one which says, well, I'm going to generate all possible outputs that could result from either typing a backspace or not for every possible character. And then I'm just going to see if the target is one of that set of possible outputs. So that's more obviously correct, but inefficient in that it looks at all possibilities. And then I can say, let's have some tests. These are the three tests that were given in the example from the problem. And I can ask the system, generate some more tests, and maybe it can be clever in the way that it comes up with the good tests for this particular problem. And then I can say, now try these two approaches. And yes, the obviously correct one takes 10 times longer, but they both pass all the tests. So that gives me some confidence that the efficient one implements the same function as the more obviously correct one. And then I can go through and say, well, is it better to scan right to left or left to right? And part of the key to understanding how this works is saying, if you scan left to right, you never know, should I output a character or should I backspace over it? But if you scan right to left, it's always the case that I can't output a character if it's not the one that's expected, because there's no further possibility to backspace over it. So you want the system to recognize that, write a function based on that. We'll skip over all the details. I wanted to show here the system giving a very long and detailed explanation, sort of a proof of why it's correct. But the details really aren't that important. What is important is that you can have a conversation with it. And here it says you can have a recursive version that tries all possibilities, or you can show that you can take a greedy approach and that will always work. And then you said, well, if the greedy approach always works, then it doesn't have to be recursive, and I won't have to worry about overflowing the stack. So I can write this non-recursive version. And then I can go back and say, that first version used lists rather than strings. Was that a good idea? And the answer is yes, because Python strings are immutable and lists can be popped. And it can finally come up with this version, which is sort of a third the size of the original and is more clear and precise. And so we hope we could arrive at something like that. So that's the imagined conversation. And the question is, can we get there? Can we get it to be right by training it better? And what processes would lead it to be able to have that kind of conversation? And I'm encouraged. And here's a collaboration that was posted by this guy, Daniel Tate. He said, I asked this system to create a game for me, and it was able to do it. So he said, can you invent a logic puzzle similar to Sudoku that doesn't currently exist? And it came up with an example. He didn't like that. So he said, invent another one. And it came up with this one. And then he said, that seems like a fun game. Can you make a playable version using HTML and JavaScript? And it could do that. And then it said, can you make it a little bit prettier with some CSS? And it did that. And here's the game. So there's this array of numbers, and on the rows and columns, there are totals that you're trying to hit. And the idea is you delete some of the numbers so that all the totals add up in each row and each column. And that was what the program produced. And then he went back and forth a little bit to say, let's make it a little bit prettier. He didn't think this was beautiful enough. And this idea of circling the ones that you're going to keep and Xing out the ones that you want to get rid of, that seemed like a nicer approach. So in the end, he got a program. He could have written it himself. He could have come up with the idea himself, but the system did maybe half the work, and he did half of the work. And that was a great collaboration. So how can we make this type of collaboration better? And so remembering that writing code is not enough, we want to look at the whole software lifecycle and say, can we speed up that whole cycle? You start with a strategy, a design, and mostly what we've been looking at so far has been focusing so tightly on this development part of writing the code. But that's just one part. You have to go on to testing and deployment and maintenance. And all these parts are important. And the development is maybe a third, maybe less. So, so here's a picture of that life cycle. And notice that at every step, you've got teams of people involved, and you've got documentation that's produced. And there's only one of the steps where you're producing some code or maybe a neural net. And the cool thing about the neural net is you can backpropagate. If there's an error, you can go back through the parameters and adjust them to eliminate that error. But you can only do that through the neural net. You can't do that everywhere else. And so I'd like to see a system where you can backpropagate through everything. If the designers came up with a strategy for the user interface, and now the world changes somehow. Suppose people are using devices with different size screens. So the assumptions that were in that original document are off. I want the system to be able to notice that error and backpropagate through everything. I don't want these design documents to be dead that are stored on a shelf somewhere. I want them to be live and to be interrogated by the system and to be updated when necessary. And I think if we have that, everything will be a lot more flexible, more responsive to the user. So one great example of this approach is by Danny Tarlow and his team at Google, a system called Didact. And the key here was that it was trained on the process of software development rather than just on the final code that solves the answer. And so if you look at the process, there's a developer, they write some code, they run some tests, they submit it for review, comments come back from the reviewer, changes are made by the developer. So the Didact system is trained in a sort of reinforcement learning manner on this whole workflow, not just the final code, but where did the code start? What are the comments that led to it being changed along the way? And that allows you to fit in better to this type of workflow and to avoid some of the mistakes that were made along the way. Another approach I think is really important is probabilistic programming. It's never quite taken off. The idea behind probabilistic programming is you describe a model of what might happen, and it's probabilistic because there is uncertainty in the world. And it's relational rather than just saying, here's how to translate inputs to outputs. It's saying, here's the measurements I have, and here's what I know about the relationships between things. And maybe I only know the output and I don't know the input, but I should still be able to describe that and then have the system use kind of Monte Carlo approaches to be able to write code that can optimize based on this probabilistic model. And so I think that will be important for a lot of these wicked type problems that don't have a deterministic specification. The idea of hierarchical decomposition is very important. And we've seen that where as a problem gets larger, as there are more tokens, the large language models tend to break down. And the traditional approach to that is hierarchical decomposition. Let's say, let's decompose the problem into sub pieces, solve those pieces individually, and then solve the problem of combining them. And this work with Parcell, done largely at Stanford, takes that approach. And I think that's going to be crucial to making success and being able to scale up where we can go. And here's just some examples of how that system works, how it can take multiple different languages, a robotic planning language, a theorem proving language, and it's fluent in the Python language and so on. And it is able to take each one of those, understand and translate between English and the formal language and go back and forth and then combine them together. And I think this idea of code is a very powerful language. So English is an amazing language, and all these other natural languages are amazing. And the large language models learn so much just from our history of what we've written down. But code also has a special point. And we've seen models like PaLM 2 take advantage of that to say, because there's been this consistent problem that the large language models just aren't very good at arithmetic. They can do 1 and 2 digit numbers, but when you get into the 3 or 4 or 5 digits, they tend to make mistakes. And recognizing that, Bard will, when given a problem, will write a piece of code to solve it. And here it's done that in one sense, it's done that exactly right. It's taken this problem. If I sell 378 apples for 39 cents each and 224 oranges for 43 cents each, how much do I make? It wrote a program, calculate earnings, that does that exactly right. Unfortunately, it didn't quite get the connection between the code that it wrote and the way it describes it exactly right. And it ends up saying you'll make 243 and 74 cents when it should have said 243 and $74, right? So that conversion between cents and dollars, it messed that up in the process of going into and out of the code. So we need to just do a little bit better on using the codes as a check, but making sure we understand how that transition goes from the general model to the specific code model. And I think we're almost there. And I just want to say, sort of as a last point, that this idea of compression encourages generalization. And so what do I mean by that? Well, so there's a lot of stuff happening out in the world. And most of what gets into a large language model comes from what is written down in books and on the web and so on. And so somebody decided this was important enough to write about, and that's what gets put into the model. So that's one part of compression. And whether it's written language or photos or video, somebody had to decide this is worth putting into the model. And then we have a further point of compression where we say our models are going to have a certain number of parameters, whether it's a certain million or billion. If there were too many parameters, then the model would just memorize the input exactly and would not be able to generalize. If there are too few parameters, then it can't hold all the information it has, and useful information starts to drop out. So you've got to get that just right to get the right level of generalization. And then there's this further step of going from a question to an answer through an intermediate representation that generates code or some formal language. And I think that's a really useful step. And we've seen some examples of that. And it's useful because, yes, the intermediate language could just be English or some natural language, but then we have no way of verifying that it's right. You take a paragraph of English, you can kind of ask, does that make sense? But you can't run it and execute it and get an output, and you can't verify it for syntax errors or runtime errors. But with a piece of code, you can. And so forcing your answers to go through code gives you this extra level of testability and reliability. And so I think we'll see more and more of that. And maybe, here I show Python and NumPy as the intermediate language. It doesn't have to be that. We can be developing other formal languages that have the property that they're checkable and executable, and have our large language models move through them. And I think that's a great area of research. It's figuring out what those languages are. So why don't I stop there and open it up for discussion? Okay. Is there a good way to use prompt for LLM to better dealing with different program lib API versions? Oh, that's a great question. Yeah, and I think that's an issue right now, because training these models is so complex that it isn't always done on a regular basis, and so often you end up with it's been trained on older versions of libraries, and it's not up to date. I guess the best thing you can do is just make sure you specify version numbers in your description, and say I want such and such an API version 3.4, and make sure you pay attention to the version number. And so bringing that to the model's attention is a good way to do that. But the models aren't built to consistently worry about that in the way that, say, a Kubernetes container is. So I don't have a great answer right now. Got an answer from Bard for Hugging Face, but Bard just gave me some code for old Hugging Face version. Yeah, right. So that's going to be a problem until the models are updated to the latest versions. And we've seen some places where some of the systems are now trying to do that, are trying to put in a fine tuning to keep things more up to date. So hopefully in the near future that will work out better. Question: I want an LLM that specifically knows about recent Flutter, not old Flutter. How hard is it to get it to prioritize modern state of the world? So I think that's the same question. Can the relative age of training data inform the LLM for bias? Yeah, that's really important, and that's always been true, right? So I've been involved with Google Search for 2 decades now, and we've always had this trade-off of how much should we trust old versus new. You have more data on the old, more signals on whether people trust it or not. And then there's a new, and maybe the new is better and up to date, but maybe the new just comes from spammers, and we should stick with the old and reliable. So that's been a problem for search optimization, and it continues to be a problem for these large language models. So it wouldn't be enough just to say, let's attach a date to everything and trust the more recent stuff more. You want to look at the more recent, but you also want to worry about is this spam, and you want to not lose the high quality stuff just because it's old. Well, you do a new course like your Udacity Design of Computer Programs, CS 212, but showing how you would use LLMs Copilot. Yeah, that's really interesting. I had a lot of fun doing CS 212 at this Udacity class. I'd like to do something like that again. And I think you're exactly right that, I sort of used bare bones Python in that class because I didn't want to have it focus on specific technologies. I wanted it to get at kind of the core of what programming is. But as I'm saying now, maybe what programming is has really changed, and maybe there should be a class like that. So I've got a few notebooks up on my PyTudes site on GitHub, and there's a couple of them that start getting into large language models. I was playing one with one over the weekend, a little game that Sergey Bolonji, a professor, came up with, and so the game was think of two words where one word you get by just dropping a single letter from the other word, and then write a crossword puzzle clue for that, and see if people can guess what the two words are. And so you can easily say, well, what pairs of words are in the dictionary that are where one drops one letter from the other? But then, you get things like cats and cat, where this cat drops the S from cats. And that's not really interesting because they're too closely related. So I said, I want to come up with interesting pairs that are not closely related. What's the easiest way to do that? Oh, I'll just download some word embeddings and then create all pairs and sort by the largest distance of the word embedding. So then you get two words that are one letter off, but are very different from each other. And that seemed to work. So that was just a super simple example. And I think it's interesting to go back. And so you make a great suggestion. I should take some of the examples from 212 or take some new examples and say, how would you address them today? That's quite different from how they were addressed a decade ago. So thanks for that suggestion. Please expand on the Monte Carlo methods for programming. Okay, so here's this idea of you observe something in the world, and when we write a regular program, we say we're going to give you the input, and the program's going to compute the output. Sometimes you say, well, the input's hidden. We don't know what that is. The input is the state of a patient's health, and then the output is their blood pressure and their results on these medical tests. And you want to say, what's the input given the output? So that's not like regular programming where you go in the forward direction. Is where you're kind of making inference in the backwards direction. And one way to do that is the Monte Carlo approach. Is named after the casino in Monte Carlo, where you have gambling games where you roll the dice or spin the roulette wheel. And so you say, let's take a random possible start state and then run it according to the rules of the game and say, does that produce the output that I observed? If so, then that's a possible start state. And then you just do this thousands or millions of times. And now you get a probability distribution over here's the likely possible starting states that could end up in the correct output state. So it's kind of rolling the dice because you don't know where you are, and then computing where you likely arrived at based on that. Is it reinforcement learning training getting over supervised learning approaches for training LLMs? Yeah, so that's really interesting. So I think the big breakthrough for LLMs is that we were able to mostly train them with self-supervised learning. So what does that mean? It means we gave them a bunch of text, and normally in supervised learning, you have a person come through and say, here's a problem and here's the answer. That's too hard and expensive to hire people to do all of that. So instead, we said, we're going to self-supervise. We're going to make up problems by saying, here's a sentence. We're going to blank out one word in the sentence and ask the system to guess what that word is. So it's supervised in the sense that there's an input, a sentence with a blank in it, and an output, the correct word to fill in the blank, and the system has to guess that correct output. But we didn't have to do any work because you can automatically blank out any word you want. So it's really easy to come up with these lots of supervised training examples. And that works pretty well. So it learns by just filling in the blanks of the words. It learns what these words mean, more or less. It learns the syntax of English. It learns some degree of argumentation, as Paige was describing in the video earlier. But sometimes it's not quite enough, right? Because sometimes there's lots of words that could fill in the blank, or sometimes you want to evaluate not just what's the one word here, but what's a whole possible paragraph. And they are just kind of looking at filling in the blanks doesn't tell you the right answer. So we do this reinforcement learning with human feedback, which means we ask the system a question, sort of after we've trained it up on the fill in the blank one at a time. We ask the system a question and say, come up with two answers. And then we show that to a human judge and say, which of these two answers is better? And then we adjust the system so that it produces more of the better one. And having that human in the loop is important because we don't have anything that can answer. We don't have a supervised way of saying which is better, these two. So the human has to be there. And then the reinforcement learning says, what led to this? So supervised learning says we're only looking at one step at a time. Reinforcement learning says we're looking at multiple steps. You generated a whole sentence or a whole paragraph. And now we're just saying this is better than that. And the reinforcement learning has to say, given that feedback of this one was better, which steps along the way were the crucial steps that led me to get there? And that's how we improve these answers on paragraph level questions. And that's how programs that play Go or chess learn to make better moves, only being told, did you win or lose the game in the end? And they can figure out which step along the way was the most important step.
Hey, Peter, it is great to have you here. Thank you so much. I've got a question for you.
Great.
As good engineers, we kind of know that one of our jobs isn't just to look at the rosy side of everything, but it's also to look at the risks, to look at the pitfalls, and to figure out how do we mitigate those risks and pitfalls. And I guess my question is, what are those risks when we're talking about using machine learning systems or LLMs or whatever as we're bringing it into this coding process? And then what do we do about it?
Right. So I think that's right. So I think there's some risks specifically from the technology. I think more of the risks really come from the problems rather than from the technologies or the solutions. And I think there's a lot of confusion about that. So people are saying, oh, I'm worried about these AI programs because they can make mistakes. And it wasn't the AI program's fault. It was that you're asking it to solve problems in which it's much harder and it's easier to make mistakes, right? And so any result could have a problem, right? So there was a lot of discussion over these AI systems that help judges make parole decisions. So they predict, is this defendant going to recommit a crime? If they are, if the prediction is that they are, then the judge will be less likely to let them have parole. And so a couple of things happen. One is you say, how well do these systems perform? And the answer is, well, pretty well. And in fact, they do better than judges with these kind of fancy AI systems. And even a simple system, which has, a simple system that could fit in a 280 character tweet, that also does better than a human judge, right? So the simple system could be, if the defendant has 2 prior convictions or their age is such and such and they have something else, then yes, else no, right? That performs better than a human judge, right? So you blame the AI system when it's not perfect, but it is doing better than the alternatives. Now, the other thing you want to worry about is not just the overall performance of the system, which gets to a pretty good level, but also the fairness of the system. And there it starts to get controversial because you start asking, well, what do I mean by fair? Well, one thing you could mean by fair is calibration, saying, if I say you're 60% likely to recommit a crime, then that should be equally true whether you're black or white or male or female. And North Point, the company that made this system, says, well, look, we did this test, we're well calibrated. It's almost the same regardless of what group you're in. Therefore, we're fair. Stop bothering us. ProPublica, the journalist who criticized them, said, yeah, you're right. You're well calibrated, but I don't think that's the most important point for fairness. I think the most important point for fairness is equal harm. So when you do make a mistake, either false negative or false positive, who does it hurt? And then they showed that it hurt black defendants twice as much as white defendants. And so they said, that's why we think you're not fair. Now, as an engineer, you might say, okay, there's two metrics. Let's just optimize both of them. Unfortunately, the way the math works out, that's just not possible, in that the two metrics are always traded off, one versus the other. And so now you're left at this point where the answer for what's right is not really a programming question or a math question. It's a societal question of, what do we as a society think is fair? And if you could tell me that, then I could go implement it. But that's what we're arguing about, is that we don't know what's fair. So I think in cases like this, what's really important is bringing all the stakeholders into play. So very early on, don't just say, oh, well, I got an algorithm that's really fast. It's order n, so I'm going to implement that. But say, what is it that we really want? And who's being hurt? And who are the stakeholders? And typically, you look at this at three levels, right? So you say, first, I want to build a system for the user. In a case like this, who's the user? Well, it's the judge. So you say, well, I want the judge to have a nice display with pretty charts and graphs and so on. And, the font should be really pretty and the output should be clear. Yeah, great. But don't end there. Then say, well, who else is involved? Well, the other stakeholders are the defendants and their families. And if someone recommits a crime, it's the victims and their families. And so take them into account, take their viewpoints into account. And then look at society as a whole. And what is the effect of mass incarceration or discrimination at a societal level? And so as an engineer, you thought my job was just to make a pretty screen for the judge. But really, you want to say my job is much larger than that. I have to take all these things into account. Or, similarly, if I'm building a self-driving car, yeah, I want the person in the car to have a great experience. But the other drivers and the pedestrians, I'm also responsible for. And at a societal level, it's, am I causing more traffic? Am I causing people to live farther out in the suburbs and disrupt urbanization? Are people losing their jobs? Those are all parts of the problem too. So kind of expanding your viewpoint on what's important, I think, is one of the key lessons.
Great. Thank you very much.
We'll integrate LLM outputs to a knowledge graph, improve the performance of LLM for coding. Yeah, so that's a great question. I've been doing AI before it was cool. And in the 80s, we were essentially building knowledge graphs. And we didn't have this idea, there was no Wikipedia to download and so on. So it's kind of, we had to build everything by hand. And we were limited in how far you could go. And we felt we hit this asymptote of, you get to the point where if you add one more fact, you're as likely to break as many things as you are to fix. So there are huge advantages to just using text, which is kind of freely available in mass quantities. But there are also advantages in having something that's better curated and which you have more trust in. And a knowledge graph is one way of doing that. I think it's not the only way. I think another approach is to integrate out third-party data sources or APIs, right? So, it makes sense that you should be able to ask a large language model, what's the capital of France? And it should know Paris. But I don't think it makes sense to expect a large language model to say, what's the capital of every county in every country in the world? I think it'd make more sense for the large language model to answer that by saying, well, I don't know, but I know a reliable atlas where I can look that up. And so I would like to see more of that type of integration. And some of it might be a knowledge graph that we've built and put together, but more of it, I think, might be just these third-party APIs to say, for this question, here's where I want to go to try to get the answer. Let's see. Do we have more questions?
Hi,
Hi.
Roida here, and I've been a huge fan of your work. I studied a lot of the courses that you taught on Udacity, and I gained a lot of knowledge. I'm really an advocate of democratizing AI, and I would like to know your advice on how to make it more accessible for other people. Thank you.
Yeah, that's great. I think we've definitely gone a long ways towards doing that, in that, it used to be you had to be an expert programmer and you had to sort of go through grad school to be able to even understand how any of the tools work. Now we've got these interfaces where you can ask these large language models anything and you're interacting with them. I think, and we also have some tools that make it easier for people to understand what's going on. So to me, education is really the key to democratization, to show people this is how the technology works, this is how it affects your life, and you can be a part of it. It's not something that these experts way out there do. This is something that you can do. And so things like the pair groups explorables, where you can play around and build a little system to do classification. So build a system that says, well, this is one signal and this is another signal, and I'm going to build a visual system that recognizes that. And in 5 minutes, you can do that, and you kind of get the idea that one, it's possible for me to do that, and two, how do those systems break? Maybe I train it and it starts picking up the background rather than picking up the foreground. So now that that's a possible failure mode for these types of systems. So I think making systems that are easy to get started, that are accessible and interesting to people, and just pushing that and showing that someone like you can do this. And that's something I've tried to do throughout my career is to welcome more people in, and I'm glad I was able to, that you were able to connect with that, and other students have. And I think we need more of these types of introductory materials to get people started, because once they get started and they get excited, then they're on the right path and they can get there. But it's this introductory part to tell people this is something that could fit for you. It's not just for these other people. I think that first step is the most important one. What are near future trends regarding LLMs, in your opinion? One of the things I'm really excited about is this multimodality, and Paige mentioned that. So I said that we have this kind of compression that we write down what we think is important about the world, and then we train on that. And so far, most of our systems are built on either on text or on images. But I think when we get another order of magnitude increase in processing power, then we'll be able to do videos as well. And I think that's interesting, because I think video is a less biased view of the world. When I write something down, it's what I think is important, and I wrote it down. When I take a photo, I click the shutter and point the camera in the direction that I think is important. But with video, sometimes it's just a stream that's just coming. And so it's more, here's what happened, rather than here's one moment that someone wanted to capture. And so I think we'll learn a lot more about the world when we have access to video.
Hello, this is Noble. Thanks so much for such an insightful talk. This is a general machine learning related question, but going off of that theme of fairness bias that was asked earlier, there's a tension in sort of enterprise context or sort of real world context. There's a tension between accuracy and fairness or bias, right? When practitioners try to apply these concepts in the real world. So for example, when you constrain optimization for fairness or bias, you sacrifice performance or accuracy. What's your thinking behind these trade-offs, and how, what's your sort of guidance there or counsel there?
I don't think that's necessarily a trade-off, right? So I mentioned there are cases where yes, there are trade-offs. If you increase one thing, you decrease another. I think for a lot of these fairness issues, I think of the trade-off more of in development time rather than in accuracy. And there's no reason you can't improve everywhere, but you got to just make these choices of who counts. Who am I going to spend the engineering effort to try to improve the experience for? And it's definitely true in machine learning, but I think it's always been true. So anytime we make product decisions, before there was machine learning, before there were computers, we're always including somebody and excluding somebody, right? So, I sell a product, a toaster, and it comes with an instruction manual. If the instruction manual is only in English, then I've left some people out. Now, I get feedbacks from my customers, and I say, okay, I'm also going to make the instructions in Spanish. Now I'm included one more group, but there's still other groups that are left out. And every time I make that decision, so it's not really a trade-off of accuracy for fairness. It's more, is it worth the time and effort to go and get that Spanish translation? And is it worth it to then do the third and fourth and fifth language? And I think that's what enterprises have to focus on. And I think they'll see a reward from treating all their customers fairly. They'll gain new customers, and they'll gain respect from the existing customers to saying, yeah, I like that you're sticking up for fairness and that you're supporting everybody.
Thank you, Peter, for that fascinating talk. Great opening session for us. And I love that Lake will be gone slide there. So, and thank you for all the great questions coming in from the audience, from the other speakers.